Hey everybody, we're gonna do some rock identification here. And I finally figured out a way to stabilize the camera. Yeah, I am standing, so you might see my shirt. Let me tuck that in anyway. Here. Before I get into this, I just want to say, if you're still interested in going on the 2025 Baraboo Wisconsin field trip, it's Labor Day weekend and some days around there. Feel free to sign up. I'll link it below. Yeah, it does cost some money, but there's 3 different packages you can choose from. You know, whatever. Anyway, speaking of Baraboo, I will tell you this. This is Baraboo quartzite, okay? And it is finer crystalline than it is in most places. It's not to the silt level, but it's probably the protolith to this is probably a fine to medium sandstone, okay? Mostly fine. And there are some, fine sandstone, but there are some silt-sized particles in this. But we're not really here to identify the rock. That's why I told you what it was right away. There's other things I want to show you. Those of you that have been to Abelman's Gorge in Wisconsin will know of Van Hise rock. It's one of the first monuments dedicated to a geologist. You can look him up if you want. But he was one of the key people to figuring out deformation patterns in mountain ranges. Yeah, Baraboo, Wisconsin. Not the Alps, not the Himalayas, not in the Rockies. It was in freaking Baraboo, Wisconsin, which I think is amazing. But anyway, I mentioned Van Hise rock because there you see some folding and some deformation where the stress fields and the cleavage tell you where the axis of the syncline is. And the only reason why that really formed is because it, right there, it was very fine quartzite, silt size particles almost entirely. I mean, it's microcrystalline. So it was an incompetent layer between 2 competent layers. But that's the exception, not the norm. In a lot of places, when you have a level bed that folds, see, if you get competent and incompetent things, that stuff's going to move like peanut butter in a peanut butter and jelly sandwich. But if it's not, if you've got, something competent, what's going to happen is you're going to break and form gaps. And that's going to fill with whatever's available as groundwater migrates through and whatnot. And in this case, it's quartz, because even though this is purple, and the purple is caused by iron, it's still 98% sandstone. Now, I bring this up because this is one of those competent on competent layers. And this isn't that far from Abelman's Gorge. It's on public land, so I don't want to hear it. But and it's not protected. But here you see these large quartzite, what looks like brecciation in this sometimes quartz crystalline matrix here. And it's just really amazing because, well, that's what happens. You're going to experience brittle failure before you experience, or sooner than you would at like Van Hise rock. You're not going to get a lot of plastic deformation because this was already a quartzite or close to it when it started being deformed. So it was pretty competent. Like I said, it's competent on competent, So you're going to pull back on that plasticity and increase your likelihood to fail, okay? Technically, this is a fault. It's a very small one, but it's, you had a bedding, and you can see them here. Here's one bedding plane, here's another bedding plane, and that fortunately is preserved in this rock. I got lucky, that's why I took it, actually. And but the offset here is maybe a few feet, a few inches to a few feet. I don't know exactly because it wasn't in place, but if I had to guess, I would say offset here is probably about 1 to 3 feet, somewhere in there. But anyway, because, this doesn't exactly line up with this or this. You can see this doesn't notch into that. But this looks like it came off this, see? So you have this brecciated pattern. Technically, well, I guess it is a breccia, even though it's not igneous. Because it's angular pebble size and they're flat. They're not elongated. The bedding is intact. You can see it. Okay, this just moved. It's the part between the 2 competent layers that broke off. And you can see how this moved. You can see These are, it's hard to see here, but this does have striations on it. And striations, I've had people tell me striations only apply to this or that. No, striation is just a set of parallel gouges in a rock at any scale. That's really all it is. So they could be, they're a texture, they're a descriptive part of a rock. They are not an interpretive part, okay? Now, if I said these were glacial striations, that would be interpretive. But if I just say they're striations, that's not interpretive. But they are tectonic striations, not glacial. So, because this rock, remember, it was being tilted this way, and this is where the beds would have moved, causing the breccia. Now, on the other side, you can see a lot more breccia. So, yeah, I just wanted you guys to see this down here too. Look at this. Yeah, and these don't line up either. So we do have probably 1 to 3 feet of, you know, offset here. Nothing huge, but something. Because it still would have had to gone through a plastic phase, even though to break, before break, you don't just go from no stress to shatter. There is no matter how small that elasticity and plastic ranges are, they're still there. So, you know, but anyway, I just thought I'd show you a little bit of brittle failure. And I do like this back. Anyway, that's it. If you have any questions or comments, please leave them below, and I hope you guys learned something.